using the Miyawaki method to create the most diverse, futuristic, self-sustaining forest cities and forest industries and begin terraforming other planets. The Miyawaki method is a revolutionary approach to afforestation that uses native species planted densely to form rapidly growing, biodiverse mini-forests. By integrating this method into urban and industrial planning, we can envision a future where cities not only coexist with nature, but thrive because of it. Here's how we can leverage the Miyawaki method to create diverse, futuristic, and self-sustaining forest cities and forest industries worldwide. Designing forest cities. Urban greening and biodiversity integration. Pocket forests and green corridors. Embed small Miyawaki forests within neighborhoods, parks, schools, and hospitals. These microecosystems can be interconnected by green corridors, allowing wildlife movement and boosting urban biodiversity. Vertical and rooftop gardens. Adapt the Miyawaki method for vertical surfaces and rooftops. Dense, multi-layered planting on building facades and rooftops can maximize greenery in space-constrained urban areas, reducing heat islands and improving air quality. Ecosystem services and urban sustainability. Carbon sequestration and climate resilience. Fast-growing Miyawaki forests absorb carbon dioxide rapidly, mitigating urban emissions. Their dense canopy also regulates temperature and humidity, which is key for urban cooling. Water management and soil health. Deep, intertwined root systems help in groundwater recharge, reduce runoff, and improve soil fertility. This natural water management can alleviate urban flooding and reduce the need for extensive artificial drainage systems. Community engagement and education. Citizen participation. Engage local communities in the planting, care, and monitoring of these forests. Educational programs can teach sustainable practices, creating a sense of stewardship and local pride. Recreational and cultural spaces. Design these green areas as multifunctional spaces that promote mental well-being, outdoor recreation, and even cultural events, thereby integrating nature deeply into urban life. Developing sustainable forest industries. Biodiverse biomass and raw material production. Agroforestry and sustainable harvesting. Use the Miyawaki method to create managed forests that yield non-timber forest products such as medicinal herbs, fruits, and nuts. These can be integrated into agroforestry systems, ensuring a renewable supply of raw materials while maintaining ecosystem health. Innovative bioeconomy. Encourage industries to develop bio-based products, biodegradable packaging, sustainable textiles, and even biofuels, using materials harvested responsibly from these dense forests. Eco-innovation and circular economy. Forest tech hubs. Establish research and innovation centers that specialize in sustainable forestry techniques, monitoring forest health using IoT sensors, AI, and remote sensing, and refining methods for biomass conversion. Zero-waste production. Develop supply chains that use all parts of the forest biomass. Waste from one process, e.g. wood chips for bioenergy, can serve as inputs for another, e.g. organic fertilizers, creating a circular regenerative system. Global collaboration and policy support. Policy frameworks and incentives. Government initiatives. Governments can support these initiatives by offering incentives like carbon credits, grants, and tax breaks for projects that integrate the Miyawaki method. Urban planning regulations could prioritize green infrastructure. International collaboration. Develop global networks that share best practices, research findings, and funding to scale these projects worldwide, ensuring local adaptations of the method to various climates and ecosystems. Education, research, and digital monitoring. Academic and NGO partnerships. Universities and non-governmental organizations can conduct research into species selection, growth rates, and ecosystem services of Miyawaki forests, tailoring approaches to specific regional needs. Digital platforms for monitoring. Utilize advanced technologies to track growth, biodiversity indices, and environmental benefits, allowing for adaptive management and rapid response to any challenges. Vision for the future. By merging the rapid, high-density growth of Miyawaki forests with forward-thinking urban design and sustainable industrial practices, we can create urban environments that are self-sustaining, resilient, and rich in biodiversity. These forest cities and industries will not only mitigate climate change and improve quality of life, but also redefine the relationship between human development and nature. The Miyawaki method is a transformative approach to reforestation that involves planting native species very densely, which results in the rapid development of highly diverse and resilient mini-forests. By using a variety of indigenous species that are well adapted to the local climate and soil conditions, this method ensures that the resulting forest grows quickly and establishes a complex ecosystem that closely resembles a natural forest. The dense planting encourages competition among the trees, which stimulates rapid growth and enhances biodiversity, making these forests particularly effective at sequestering carbon, regulating temperatures, and managing water resources. When applied to urban planning, the Miyawaki method can be used to create what are known as forest cities. In these cities, small pockets of Miyawaki forests can be integrated into public parks, along streets, on rooftops, and even on the facades of buildings. These mini-forests not only beautify urban landscapes, but also play a crucial role in mitigating urban challenges such as air pollution, heat islands, and water runoff. By establishing green corridors that connect these dense patches of forest, cities can facilitate the movement of wildlife, enhance ecological connectivity, and create urban spaces that are both healthy and sustainable. In addition, the integration of these green spaces into urban design can foster community engagement and provide residents with accessible areas for recreation, education, and cultural activities, thereby strengthening the bond between urban communities and nature. The principles of the Miyawaki method also extend to the development of sustainable forest industries. By managing forests with a focus on biodiversity and rapid growth, industries can harvest non-timber products such as medicinal herbs, fruits, nuts, and other biomaterials without compromising the integrity of the ecosystem. This approach supports agroforestry practices where the forest is not merely a source of raw materials, but a dynamic system that contributes to a local bioeconomy. Innovations in forest technology, including the use of sensors, artificial intelligence, and remote monitoring, can help optimize the sustainable harvesting and processing of forest products, ensuring that every part of the biomass is utilized effectively and that waste is minimized. This leads to the creation of circular economies in which forest resources are regenerated continuously, supporting the production of biodegradable materials, renewable energy, and sustainable consumer goods. To implement these innovative ideas on a global scale, strong policy frameworks and international collaboration are essential. Governments can promote the adoption of the Miyawaki method by providing incentives such as carbon credits, grants, and tax breaks to cities and industries that invest in sustainable forestry projects. Academic institutions, research organizations, and non-governmental organizations can contribute by conducting studies that fine-tune species selection, growth models, and ecosystem services specific to different regions. Moreover, global networks and partnerships can facilitate the sharing of best practices and technological advances, ensuring that the benefits of this method are realized across diverse climatic and cultural contexts. By embracing the Miyawaki method, we have the opportunity to revolutionize both urban environments and forest-based industries. The method's focus on biodiversity and rapid growth can transform urban areas into thriving, self-sustaining forest cities that offer enhanced ecological services and improved quality of life for their inhabitants. At the same time, it can support the development of innovative, sustainable forest industries that harness the natural productivity of these ecosystems, leading to a greener, more resilient future for communities around the world. Employing the Miyawaki forest method to establish the most sustainable society, naturally regenerate the Earth, and begin terraforming and colonizing Mars and other planets. The Miyawaki forest method is a groundbreaking approach to reforestation that involves planting native species very densely so that biodiverse mini-forests develop rapidly. This method has been shown to regenerate local ecosystems, sequester carbon efficiently, and create resilient natural spaces in a relatively short period of time. By employing this method on a large scale, we could create a sustainable society on Earth that naturally regenerates its landscapes and even serves as a model for establishing life-supporting ecosystems on other planets. On Earth, using the Miyawaki method involves reforesting degraded or urbanized areas with native trees and shrubs to form compact, high-density forests. These forests quickly become rich in biodiversity and offer multiple ecosystem services. They sequester carbon dioxide, stabilize local climates, improve water management by increasing groundwater recharge, and enhance soil health. When integrated into urban planning, these mini-forests can transform cities into living, breathing organisms. Cities could be redesigned with green corridors and vertical forests that not only mitigate pollution and reduce urban heat islands, but also create community spaces that foster a deep connection between residents and nature. In a society based on sustainability, every element of urban design and industrial practice would work in harmony with natural processes. The Miyawaki method could serve as a model for creating green networks that span entire cities and regions, ensuring that even the most built-up areas contribute to ecological balance. This approach would help in developing a circular economy where industries rely on renewable resources from these forests, producing bio-based materials and energy with minimal environmental impact. Such integration would not only counteract the effects of climate change, but also establish a self-sustaining cycle of natural regeneration and human development. Looking beyond Earth, the principles underlying the Miyawaki method can also inspire strategies for terraforming and colonizing Mars and other planets. Although conditions on Mars are currently harsh, with low atmospheric pressure, high radiation, and extreme temperatures, the concept of creating a rapidly developing, biodiverse ecosystem could be adapted to controlled environments on Mars. For instance, future Martian habitats could incorporate dome-enclosed biospheres where Earth-like conditions are simulated. Within these biospheres, the dense planting techniques of the Miyawaki method could be used to cultivate small, resilient forests that contribute to oxygen production, enhance soil quality through microbial activity, and even provide food resources for human colonists. By designing these controlled ecosystems with a variety of native or specially engineered plant species, scientists and engineers could gradually transform these biospheres into stable, self-sustaining habitats. Over time, these closed ecological systems might serve as the basis for broader terraforming projects, where incremental improvements in atmospheric quality and soil composition allow for the gradual expansion of life-supporting environments. This approach would require interdisciplinary collaboration among ecologists, urban planners, engineers, and space scientists to address challenges such as genetic diversity, soil regeneration, and radiation shielding. The lessons learned from regenerating Earth through the Miyawaki method could provide invaluable insights into how to design resilient ecosystems that support human life on other planets. Employing the Miyawaki method to create a sustainable society on Earth involves reforesting urban and rural areas to regenerate natural ecosystems, sequester carbon, and improve overall quality of life. These principles, when adapted to controlled environments in space, could form the foundation of early terraforming efforts on Mars and other planets, gradually transforming harsh extraterrestrial landscapes into habitable environments. This visionary approach exemplifies how integrating advanced ecological methods with modern technology can lead to a future where both Earth and other planetary bodies support thriving, sustainable communities. Formulate a plan to turn the Earth into its healthiest form and begin terraforming other planets with a Miyawaki forest method. The Miyawaki method is an innovative reforestation technique that emphasizes the rapid development of biodiverse, native mini-forests through dense planting. By harnessing this method, we can restore and transform Earth's ecosystems into vibrant, self-sustaining natural systems while also laying the groundwork for establishing life-supporting habitats on other planets. This plan is divided into two primary parts: transforming Earth into its healthiest form and pioneering terraforming initiatives on extraterrestrial bodies such as Mars. Transforming Earth into its healthiest form. Comprehensive ecosystem restoration. Urban reforestation and green infrastructure. Pocket forests and green corridors. Develop dense native mini-forests within urban settings, integrating them into parks, schools, and even along streets to combat urban heat islands, purify the air, and enhance residents' quality of life. Vertical and rooftop gardens. Adapt the Miyawaki method to create vertical gardens on building facades and rooftop forests. This maximizes green space in densely populated areas and contributes to improved urban microclimates. Rural and degraded land rehabilitation. Reforestation of degraded areas. Apply the Miyawaki method to restore deforested and degraded lands. The rapid growth and biodiversity of these mini-forests help stabilize soils, improve water retention, and rebuild lost habitats. Habitat connectivity. Establish interconnected green corridors between restored areas to allow wildlife migration, enhance genetic diversity, and support overall ecosystem resilience. Integrating sustainable societal practices. Circular bioeconomy and renewable resources. Sustainable harvesting. Use the productive yields of these forests, such as fruits, nuts, medicinal herbs, and other non-timber forest products, to support local economies and provide renewable resources without depleting natural capital. Biomass and bioenergy. Develop eco-friendly biomass energy projects that use forest byproducts in a closed-loop system, reducing waste and lowering carbon emissions. Policy support and community engagement. Government incentives. Advocate for policies that offer tax breaks, carbon credits, and grants for urban reforestation and land restoration projects based on the Miyawaki method. Educational outreach. Engage communities through educational programs and participatory planting initiatives that foster environmental stewardship and public investment in nature's health. Monitoring, research, and adaptive management. Technological integration for ecosystem health. Digital monitoring systems. Utilize remote sensing, IoT sensors, and AI-driven analytics to monitor forest growth, biodiversity levels, and environmental impact in real time, enabling adaptive management and timely interventions. Research collaborations. Foster partnerships among academic institutions, environmental NGOs, and government agencies to continuously refine species selection and planting techniques, ensuring each project is optimized for local conditions. Terraforming and establishing habitable ecosystems on other planets. Establishing controlled biospheres. Dome-enclosed habitats. Simulated environments. Create dome-enclosed biospheres on planets like Mars where Earth-like conditions, temperature, humidity, and pressure can be artificially maintained. These controlled environments serve as experimental platforms for testing the Miyawaki method beyond Earth. Initial soil and water management. Develop substrates and water management systems that mimic Earth's fertile soils and hydrological cycles, forming the foundation for plant growth in extraterrestrial conditions. Adapting the Miyawaki method for extraterrestrial conditions. Species selection and genetic engineering. Resilient native species. Identify or engineer plant species that can thrive in controlled Martian biospheres, taking into account factors like reduced gravity, radiation, and atmospheric composition. Dense, layered planting. Employ the Miyawaki approach of dense, multi-layered planting to rapidly build biodiverse mini-forests that contribute to oxygen production, soil development, and nutrient cycling. Ecosystem services in closed-loop systems. Oxygen production and carbon dioxide recycling. Dense forests can act as natural oxygen generators while absorbing carbon dioxide, crucial for maintaining breathable air within closed habitats. Food and resource production. Develop food forests within biospheres that yield edible fruits, nuts, and other produce, providing a renewable food source for inhabitants and reducing reliance on resupply missions from Earth. Overcoming extraterrestrial challenges. Radiation protection and environmental control. Shielding and structural support. Implement advanced materials and shielding techniques in biospheres to protect growing forests from harmful cosmic radiation and solar flares. Atmospheric regulation. Continuously monitor and adjust the balance of gases within the biospheres, ensuring a stable environment conducive to both plant and human life. Incremental ecosystem expansion. Phased growth strategy. Begin with small, contained experimental plots using the Miyawaki method and gradually expand the biospheres as the ecosystems stabilize and prove their resilience over time. Interdisciplinary collaboration. Encourage collaboration between space scientists, ecologists, and engineers to solve emerging challenges and optimize the growth of extraterrestrial ecosystems. Implementation, collaboration, and future outlook. Global and interplanetary collaboration. International initiatives. Establish global networks that bring together governments, research institutions, private industry, and space agencies to coordinate efforts in reforestation and terraforming projects. Shared research and technology transfer. Facilitate the exchange of knowledge and technology between Earth-based projects and extraterrestrial initiatives, ensuring that breakthroughs in one realm benefit the other. Phased rollout and pilot projects. Earth pilot projects. Launch pilot projects in diverse environments, from urban centers to degraded rural landscapes, to demonstrate the effectiveness of the Miyawaki method in regenerating ecosystems. Extraterrestrial test beds. Develop initial biosphere projects on Mars or other candidate planets as experimental test beds, using insights gained from Earth-based projects to guide design and implementation. Long-term vision. Holistic planetary health. Aim to transform Earth into a vibrant, resilient, and self-sustaining planet that serves as a model of ecological restoration and sustainability for the entire solar system. Pioneering interplanetary habitats. Use the lessons learned from Earth's transformation to gradually extend life-supporting ecosystems beyond our planet, paving the way for a future where humanity can thrive in multiple environments. By leveraging the Miyawaki forest method, we can transform Earth into its healthiest, most resilient form, creating urban and rural landscapes that are rich in biodiversity, provide critical ecosystem services, and support sustainable human societies. Furthermore, adapting these principles to controlled biospheres on other planets offers a pioneering pathway to terraforming and establishing life-supporting habitats beyond Earth. Through global collaboration, technological innovation, and a phased implementation strategy, this comprehensive plan represents a visionary yet pragmatic approach to planetary regeneration and interplanetary colonization. Launching colonies on Mars, Moon, and other planets by utilizing the Miyawaki forest and production method. Space colonization requires the creation of resilient, closed-loop ecosystems that can generate oxygen, produce food, and recycle waste. The Miyawaki forest method, a technique for rapidly establishing biodiverse, dense mini-forests, offers an innovative approach when adapted to extraterrestrial environments. By integrating this method with advanced production systems, we can develop colonies that not only support human habitation but also transform barren landscapes into thriving, self-sustaining habitats. The Miyawaki forest method and space colonization. Principles of the Miyawaki method. Dense, rapid growth. The method involves planting a variety of native or specially engineered species at high densities to promote fast, competitive growth and rapid ecosystem establishment. Biodiversity and layered canopies. By mimicking natural forest structures, the Miyawaki method creates multi-layered ecosystems that maximize the use of space and resources. Ecosystem services. These dense forests can serve as natural oxygen generators, carbon sinks, and producers of biomass, all of which are essential for supporting human life in closed habitats. Integrating production systems. Agroforestry integration. Combining forestry with sustainable farming practices ensures that these ecosystems provide food, raw materials, and medicinal plants. Circular production. Waste recycling, biomass conversion, and renewable energy generation are integrated into the system to create a self-sustaining, zero-waste colony. Adapting the Miyawaki method for extraterrestrial environments. Controlled biospheres and environmental simulation. Dome-enclosed habitats. The first step is to build controlled, dome-enclosed biospheres on Mars, the Moon, or other planets. These habitats simulate Earth-like conditions, temperature, humidity, and atmospheric pressure that allow terrestrial plants to thrive. Environmental control systems. Advanced systems will manage light, water, and nutrients, ensuring that the mini-forests receive the optimal conditions they require for rapid growth. Radiation shielding. Structures will incorporate protective shielding to reduce the impact of cosmic radiation and solar flares, safeguarding both plant and human life. Specialized plant species and genetic engineering. Species selection. Identify or engineer plant species that are resilient and adaptable to controlled extraterrestrial conditions. These may include fast-growing trees and shrubs that not only produce oxygen, but also yield edible fruits, nuts, and medicinal compounds. Genetic adaptation. Research and development in genetic engineering can enhance the stress tolerance of plants, ensuring they survive in environments with lower gravity or different atmospheric compositions. Layered ecosystems. Using the Miyawaki technique, plants will be arranged in layered formations to optimize space usage, light absorption, and nutrient cycling within the biospheres. Launching colonies. Phases and implementation. Phase 1. Robotic and automated precursor missions. Site assessment and preparation. Robotic missions will assess landing sites on Mars, the Moon, or other celestial bodies, gathering data on soil composition, radiation levels, and environmental conditions. Automated construction. Robots will construct the initial dome habitats and establish basic infrastructure for water, air, and nutrient delivery. Initial planting. Early plantings using the Miyawaki method will be initiated in these controlled environments, establishing the first mini-forests as pilot projects. Phase 2. Establishing controlled biospheres and life support systems. System integration. Once the pilot mini-forests show successful growth, additional controlled biospheres will be expanded to include integrated agroforestry and production systems. Life support augmentation. These biospheres will begin to generate oxygen, capture carbon dioxide, and produce food, reducing reliance on supplies from Earth. Monitoring and adaptation. Continuous monitoring using IoT sensors and AI-driven analytics will help adjust environmental conditions and optimize plant growth and resource production. Phase 3. Human colonization and ecosystem expansion. Human habitation. As the ecosystems mature, human colonists will move into these habitats, living in close integration with the mini-forests that provide essential ecosystem services. Expansion and scaling. The initial biospheres will be expanded, interconnected, and gradually evolved into larger, self-sustaining colonies that mirror Earth's ecological balance. Interplanetary networks. Similar techniques can be replicated on multiple celestial bodies, creating a network of interconnected colonies that share knowledge, technology, and resources. Integrating production systems within the colonies. Food production and agroforestry. Multi-layered agriculture. Incorporate food crops into the understory of the Miyawaki forests, allowing for simultaneous production of timber, fruits, vegetables, and medicinal plants. Vertical farming. In areas where horizontal space is limited, vertical farms and green walls can be integrated with the forest system to maximize output. Material production and waste recycling. Biomass utilization. Harvested biomass from the forests can be converted into biofuels, construction materials, and even biodegradable plastics, creating a circular economy. Waste-to-energy systems. Organic waste from human habitation and plant debris will be composted and recycled, feeding back into the nutrient cycle and supporting continuous plant growth. Energy and resource independence. Renewable energy integration. Solar panels, wind turbines, and other renewable energy sources will power the biospheres, reducing dependency on Earth-based energy supplies. Water recycling. Advanced water recycling systems will ensure that every drop is reused, maintaining a closed-loop system that sustains both the flora and human inhabitants. Technological, scientific, and policy considerations. Research and development. Interdisciplinary collaboration. Scientists, engineers, ecologists, and space experts must collaborate to continuously improve the adaptation of the Miyawaki method for extraterrestrial conditions. Pilot studies and feedback. Data from early pilot projects will inform adjustments in species selection, environmental controls, and production methods, ensuring that each subsequent phase is optimized for success. Policy and funding. International partnerships. Collaboration between space agencies, research institutions, and private enterprises will be essential to fund and implement these ambitious projects. Incentives for innovation. Government policies and international agreements should promote investment in space colonization, renewable energy, and sustainable biosphere technology. Utilizing the Miyawaki forest and production method as a core component of extraterrestrial colonization offers a promising pathway toward creating self-sustaining habitats on Mars, the Moon, and beyond. By establishing controlled biospheres that replicate Earth-like conditions, integrating advanced production systems, and scaling these initiatives in phases, from robotic precursors to full human colonization, can transform barren landscapes into thriving ecosystems that support life. This approach not only provides essential resources such as oxygen, food, and raw materials, but also establishes a sustainable, circular economy that can underpin humanity's expansion into the cosmos.